April 15th, 1942, Provincetown Harbor, Cape Cod, Massachusetts. Coast Guard Coxswain Harold Mattingly gripped the wheel of his patrol boat as it ran hard aground on a sandbar 300 yards from shore. The tide was falling rapidly, and conventional rescue boats drew too much water to reach them. Behind him, 7 crew members faced the prospect of spending the night stranded in frigid Atlantic waters. From the beach, an ungainly vehicle splashed into the surf. It looked like someone had mounted a boat hull on truck wheels, creating something that belonged neither on land nor at sea. The experimental craft churned through the water at 6 knots, reached the stranded patrol boat, and took the crew aboard. Then it drove directly onto the beach without stopping, climbed the sand dunes, and delivered the rescued men to the Coast Guard station. What Mattingly witnessed that morning was the birth of a vehicle that would revolutionize amphibious warfare. Within 3 years, 21,000 DUKWs would be driving from ship to shore across every major invasion beach of World War II. The engineering principles demonstrated that rescue would enable Allied forces to land on hostile shores without ports, without docks, without anything except the ingenuity of 3 civilians who had solved a problem the military said was impossible. The origins of this revolutionary vehicle lay not in military doctrine, but in a question that seemed absurd to experienced naval architects. Could a truck swim and a boat drive? For decades, the answer had been an emphatic no. The requirements were contradictory. Ships needed deep hulls for stability in rough water. Trucks needed ground clearance for obstacles and traction. No single vehicle could excel at both functions without compromising performance fatally in each. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The breakthrough came from an unlikely source. In early 1942, Rod Stevens was known primarily as a yacht designer, creator of elegant sailing vessels for wealthy clients. Dennis Pouliston was a British sailor and naturalist studying bird migration patterns along the American coast. Frank Spear was a research engineer at the Massachusetts Institute of Technology, working on automotive suspension systems. None of them were military engineers. None had experience with amphibious vehicles. Their collaboration would produce the most important tactical innovation in amphibious warfare since the invention of the landing craft itself. The initial concept emerged during a meeting at the Sparkman and Stevens Yacht Design Office in Manhattan on February 23, 1942. Pouliston had been discussing the challenges of bird research on coastal islands, areas accessible only by boat but requiring vehicular transport once ashore. Stevens, accustomed to solving problems through elegant design, sketched a preliminary concept. A standard truck chassis fitted with a watertight boat hull. The engine would power both wheels for land operation and a propeller for water operation through a transfer case. Spear's engineering background immediately identified the critical challenges. Weight distribution would be crucial. Too much weight forward and the vehicle would dive nose first into waves. Too much weight aft and it would be unstable on land. The hull shape would determine seaworthiness, but also affect ground clearance and approach angles. The propulsion system needed to transition smoothly between wheel drive and marine propeller without operator error causing catastrophic failure. Within hours of that initial meeting, the 3 men had outlined the fundamental engineering principles that would define the DUKW. The hull would be boat-shaped but mounted high on the truck chassis to provide adequate ground clearance. The engine would be a standard automotive unit, reliable and familiar to military mechanics. A transfer case would direct power to either the wheels or propeller, never both simultaneously. Most critically, the vehicle would be designed for simplicity of operation. Any truck driver should be able to learn its use within days, not months. The military's initial reaction was predictably skeptical. The Office of Scientific Research and Development had received hundreds of proposals for amphibious vehicles, most from inventors with limited understanding of either marine or automotive engineering. Admiral Emery Land, chairman of the Maritime Commission, dismissed the concept without seeing detailed plans. "Boats are boats and trucks are trucks," he wrote in response to the preliminary proposal. "The Navy has no interest in compromises that excel at neither function." But the National Defense Research Committee, under the direction of Vannevar Bush, operated with greater flexibility. Bush understood that the war would require innovations beyond traditional military thinking. When the trio presented detailed engineering drawings and stress calculations, the committee authorized construction of a prototype at a cost of $50,000. The project was designated DUKW, using military nomenclature. D indicated the year 1942, U meant utility, K meant all-wheel drive, and W meant dual rear axles. The first prototype emerged from a converted garage in Newburyport, Massachusetts on June 2, 1942. Built on a GMC CCKW truck chassis, it stretched 31 feet in length and 8 feet in width. The hull was constructed from welded steel plate, forming a boat-shaped compartment that enclosed the entire truck chassis. A marine propeller connected to the truck's transmission through a transfer case allowed the vehicle to swim at 6 knots. On land, it could reach 50 miles per hour on highways. The prototype's first water trials revealed immediate problems. The vehicle was nearly impossible to steer in water. The rudder was too small, providing insufficient control at low speeds. The bilge pump could not keep pace with water entering through various hull penetrations. Most seriously, the transition from water to land created a dangerous moment when the vehicle was neither swimming nor driving, but suspended between elements. Speer attacked the steering problem through systematic testing. He calculated the hydrodynamic forces acting on the hull at various speeds and angles, determining that the rudder needed to be nearly twice the original size. But enlarging the rudder created new problems. It increased drag, reducing water speed and fuel efficiency. Worse, it made the vehicle unstable at high road speeds, creating dangerous oscillations that could cause loss of control. The solution emerged from studying the behavior of seaplanes during water landings. Speer observed that aircraft used adjustable control surfaces to manage the transition between flight and water operation. He designed a rudder system with 2 positions. In water, the full rudder provided maximum steering control. On land, the rudder folded against the hull, reducing wind resistance and eliminating high-speed instability. The bilge pump problem required understanding the fundamental physics of amphibious operation. Water entered the hull through numerous points. The propeller shaft penetrated the hull, requiring a stuffing box that could never be completely watertight. The rudder mounting created another potential leak point. Air vents necessary for engine operation allowed water entry during rough weather. Most significantly, the transition from water to land caused tremendous stress on hull seams as the vehicle's weight shifted from buoyant support to mechanical support. Stevens applied yacht-building techniques to seal the hull. He specified marine-grade sealants at every joint, double-sealed all penetrations, and designed a drainage system that channeled water to collection points where pumps could remove it efficiently. The bilge pump system was oversized, capable of handling twice the expected water intrusion. Backup hand pumps provided redundancy if the primary electric pumps failed. The transition problem proved most challenging. When the DUKW moved from water to land, there was a critical moment when the wheels touched bottom but had not yet gained traction. During this phase, the vehicle was neither floating nor driving, creating potential for loss of control or structural damage. Pulliston, drawing on his sailing experience, recognized this as similar to the problem faced by boats running aground on beaches. The solution required understanding the vehicle's behavior during transition. In water, the DUKW was supported by buoyancy, with its weight distributed evenly across the hull. As it approached shore, the wheels would touch bottom, while the hull remained partially submerged. During this transition, the vehicle's weight shifted gradually from buoyant support to mechanical support through the wheels. The key was ensuring this transition occurred smoothly, without sudden weight transfer that could damage the drivetrain or cause loss of control. Speer designed the wheel and tyre combination to manage this transition. Large, low-pressure tyres provided flotation when partially submerged, reducing the sudden weight transfer as wheels gained traction. The tyre pressure could be adjusted from the driver's position, allowing optimal inflation for different terrain. Low pressure provided maximum traction on soft sand. Higher pressure enabled efficient highway driving. The central tire inflation system represented a significant innovation. The driver could adjust pressure in all 6 tires simultaneously while the vehicle was moving. This capability proved crucial for amphibious operations, where beach conditions varied dramatically. Volcanic sand required different tire pressure than coral beaches. Muddy riverbanks demanded different settings than rocky shores. The propulsion system underwent extensive refinement. The original design used a simple transfer case that directed engine power to either wheels or propeller, but testing revealed that smooth transition between modes required more sophisticated control. The final design incorporated a 2-speed transfer case that could direct power to wheels, propeller, or both simultaneously during transition phases. This dual power capability solved the transition problem elegantly. As the DUKW approached shore, the operator could engage both wheel and propeller drive. The propeller provided forward motion while the wheels gained traction on the bottom. Once wheels achieved full traction, the propeller could be disengaged without losing momentum. The reverse process allowed smooth entry into water from beaches. The hull design required balancing contradictory requirements. For seaworthiness, the hull needed to be deep with a sharp entry angle to cut through waves. For ground clearance, it needed to be mounted high on the chassis. For stability, weight needed to be low. For capacity, internal volume needed to be maximized. Stevens solved this through careful shaping of the hull bottom. The forward section had a sharp V shape that cut through waves efficiently. The middle section transitioned to a flatter bottom that provided stability and internal volume. The rear section curved upward, protecting the propeller and creating a clean wake. This complex shape was expensive to manufacture, but provided optimal performance in both water and land operation. Testing revealed that engine cooling presented unique challenges. Truck engines were designed for air cooling while driving. In water, at low speeds, insufficient air flowed through the radiator. The solution required a dual cooling system. Air cooling remained primary for land operation. A supplementary water cooling system drew seawater through a heat exchanger when operating in marine mode. The water cooling system used seawater pumped through a secondary heat exchanger that cooled the primary engine coolant. This prevented overheating during extended water operation while maintaining the standard truck cooling system for land use. The complexity was manageable because the systems operated independently, requiring no operator intervention to switch between modes. Electrical systems posed another challenge. Standard truck electrical components could not withstand constant exposure to salt water and humidity. Every electrical connection required sealing. Wiring needed to be routed through watertight conduits. The starter, generator, and ignition system required special protection. Marine-grade components were specified throughout, increasing cost but ensuring reliability in harsh conditions. The vehicle's weight distribution required careful calculation. The engine, transmission, and differential created a heavy concentration in the front of the vehicle. The fuel tank, battery, and spare tire added weight at the rear. Cargo capacity further affected weight distribution. The final design achieved balance through careful placement of components and ballast tanks that could be filled or emptied to adjust trim in water. By November 1942, the prototype had completed over 500 hours of testing in conditions ranging from calm harbors to rough Atlantic surf. The vehicle had proven it could operate in waves up to 4 feet high, climb beaches with gradients up to 15 degrees, and transition between water and land without operator difficulty. Performance exceeded all specifications. Water speed reached 6 knots consistently. Land speed exceeded 50 miles per hour on highways. Fuel consumption was acceptable at 8 miles per gallon on land, 4 miles per gallon in water. The Coast Guard rescue at Provincetown provided the crucial demonstration that convinced military skeptics the DUKW had performed a mission impossible for any other vehicle. It had reached a stranded vessel in shallow water, evacuated the crew, and delivered them to safety ashore. No landing craft could have operated in such shallow water. No truck could have reached the stranded boat. Only a vehicle that could excel at both functions could have accomplished the rescue. General Omar Bradley, observing the rescue, immediately understood the implications for amphibious warfare. Landing craft could deliver troops to beaches, but cargo had to be unloaded manually and transported inland by separate vehicles. The DUKW could eliminate this vulnerable transition. Supplies could be loaded on ships, transported directly to forward positions, and unloaded where needed. The beach would no longer be a bottleneck for logistics flow. The military placed its first order for 2,000 DUKWs on December 7, 1942, exactly 1 year after Pearl Harbor. General Motors was selected as the primary manufacturer, with production to begin at the Pontiac East Assembly Plant. The engineering team would work with GM engineers to adapt the design for mass production while maintaining the performance characteristics proven in testing. Mass production required significant engineering changes. The hand-welded steel hull was too expensive and time-consuming for large-scale manufacturing. GM engineers developed stamping techniques that could form hull sections from steel plate, then weld them together in assembly line fashion. The complex transfer case was redesigned for easier manufacturing while maintaining its dual-drive capability. Quality control became crucial as production accelerated. Each DUKW required precise hull sealing to prevent water intrusion. Engine timing had to be exact for proper operation in both modes. Tire pressure systems needed calibration for different inflation settings. GM developed testing procedures that verified every vehicle's amphibious capability before delivery to military units. The first production, DUKWs, rolled off the assembly line at Pontiac in March 1943. Each vehicle was tested in a specially constructed water tank that simulated ocean conditions. Operators trained on the vehicles verified their seaworthiness and land performance. Quality inspectors checked hull sealing, engine operation, and electrical systems. Only vehicles that passed all tests were accepted for military service. By June 1943, production reached 50 vehicles per month. Training programs were established to teach military personnel DUKW operation and maintenance. The vehicles were assigned to newly formed amphibian truck companies, specialized units that would operate them in combat. Each company received 60 DUKWs and trained intensively for amphibious operations. The first combat deployment came in July 1943 during the invasion of Sicily. The 458th Amphibian Truck Company landed with assault forces, using their DUKWs to deliver supplies from ships offshore directly to artillery positions inland. The vehicles performed exactly as designed, eliminating the traditional bottleneck at beach unloading areas. Within 6 months, DUKW production had increased to over 200 vehicles monthly. The engineering challenges had been solved through systematic testing and refinement. The manufacturing problems had been overcome through innovative production techniques. Most importantly, the concept had been proven in combat. Trucks could swim and boats could drive, exactly as 3 civilian engineers had envisioned on that February morning in 1942. The fundamental engineering principles established during development remained unchanged throughout production. Hull shape determined performance in water. Weight distribution affected stability in both elements. Engine cooling required dual systems. Electrical components needed marine protection. Tire pressure adjustment enabled operation on various terrain. The transfer case managed transition between drive modes. Each principle had been tested extensively, refined through practical experience, and proven in combat conditions. The resulting vehicle was neither a perfect truck nor a perfect boat, but an optimal compromise that could excel adequately at both functions. It represented a new category of military equipment, purpose-built for the unique requirements of amphibious warfare. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The success of the DUKW concept validated the engineering approach that prioritized versatility over specialization. Traditional military thinking favored specialized equipment optimized for specific functions. The DUKW demonstrated that well-designed compromises could provide capabilities impossible for specialized equipment to achieve. A vehicle that was 70% as effective as a truck and 70% as effective as a boat could accomplish missions that no truck or boat could perform. This philosophy would influence military equipment development for decades. The lesson was clear. When facing unprecedented challenges, solutions might come from unconventional sources. Civilian engineers approaching military problems without preconceived limitations could identify possibilities that military specialists missed. The key was maintaining openness to ideas that violated established doctrine. The engineering team's approach emphasized practical testing over theoretical perfection. Every design decision was validated through actual operation in realistic conditions. When problems emerged, they were solved through systematic analysis and innovative solutions. The prototype was rebuilt repeatedly until performance met requirements. Only then was the design frozen for mass production. This methodology contrasted sharply with traditional military development, which often emphasized theoretical performance over practical reliability. The DUKW succeeded because it was designed to work in real conditions, not to meet specifications on paper. Every component was tested to failure. Every system was operated beyond its intended limits. Only designs that survived this rigorous testing were incorporated into the final vehicle. The three engineers who created the DUKW had solved a problem that military experts insisted was impossible. They had done so by ignoring the conventional wisdom that trucks and boats were fundamentally incompatible. Instead, they had analyzed the specific requirements of each function and designed systems that could fulfill both adequately. Their success demonstrated the power of fresh thinking applied to seemingly intractable problems. By December 1943, over 2,000 DUKWs had been produced and deployed to theaters worldwide. They were operating in the Mediterranean, preparing for operations in France, and training for Pacific Island assaults. The vehicle that had begun as a sketch in a yacht designer's office had become an essential component of Allied amphibious capability. The engineering principles established during DUKW development would influence subsequent amphibious vehicle design for decades. The concept of dual-mode operation became standard for later vehicles. The emphasis on simplicity and reliability guided military specification development. Most importantly, the demonstration that civilian innovation could solve military problems permanently changed procurement procedures. But the greatest impact was immediate and practical. Allied forces could now land on any beach, regardless of port facilities or developed infrastructure. The DUKW had transformed amphibious warfare from a specialized operation requiring extensive preparation to a flexible capability that could be employed wherever needed. The engineering innovation had enabled strategic revolution. The vehicle that emerged from that converted garage in Newburyport represented more than mechanical ingenuity. It embodied a philosophy of problem-solving that emphasized practical solutions over theoretical perfection, versatility over specialization, and innovation over tradition. These principles, as much as the vehicle itself, would prove decisive in the campaigns ahead. The story of the DUKW's development reveals how three civilians with no military experience revolutionized warfare through systematic engineering and persistent testing. Their achievement was not a stroke of genius, but the result of careful analysis, innovative design, and relentless refinement. They had proven that the impossible was merely the untried, that engineering could overcome any obstacle, and that fresh thinking could solve problems that had stumped experts for decades. As 1943 ended, DUKWs were gathering in Britain for the greatest amphibious operation in history. The vehicles that had emerged from a yacht designer's sketch would soon carry Allied forces onto the beaches of Normandy, transforming D-Day from a military operation into an engineering triumph. The engineers who had made trucks swim and boats drive had given Allied commanders a capability that would prove decisive in the battle for Europe. June 6, 1944. Utah Beach, Normandy, France. Technical Sergeant Robert Martinez of the 458th Amphibian Truck Company watched his DUKW climb from the English Channel onto the sand at 06:45 hours. 36 fully equipped paratroopers from the 82nd Airborne Division riding in the cargo bay behind him. The vehicle's 6 wheels gained traction on the wet sand, water streaming from its hull, and continued inland without stopping. No pause for unloading. No vulnerable moment at the waterline. The engineering principles tested at Provincetown 2 years earlier were now enabling the liberation of Europe. Behind Martinez, hundreds of other DUKWs were emerging from the grey waters of the Channel, each one carrying the supplies and reinforcements that would sustain the Allied foothold in Nazi-occupied France. The vehicles represented the culmination of engineering innovation that had transformed an impossible concept into decisive military capability. What had begun as a sketch in a Manhattan office was now rewriting the rules of amphibious warfare on the most important beaches in human history. The scale of DUKW operations on D-Day dwarfed anything previously attempted. The 458th, 459th, and 460th amphibian truck companies had trained for months in Britain, practicing beach landings in conditions that simulated the Normandy surf. Each company operated 60 DUKWs, their crews drilled endlessly in transition procedures, cargo handling, and emergency repairs. The vehicles themselves had been winterized for North Atlantic conditions, fitted with additional bilge pumps, and loaded with spare parts for field maintenance. The engineering challenges of Channel operations exceeded anything encountered in Mediterranean or Pacific theatres. The English Channel in June presented rough seas, strong currents, and unpredictable weather. The distance from transport ships to shore stretched DUKW range to its limits. Most critically, the tidal range at Normandy created constantly changing beach conditions that demanded maximum flexibility from amphibious vehicles. Rod Stevens, now serving as a technical advisor to amphibian forces, had spent weeks in Britain analysing Normandy beach profiles and tide tables. His calculations showed that conventional landing craft would face severe difficulties during certain tidal phases, when the beach gradient created impossible unloading conditions. DUKWs could operate throughout the tidal cycle, driving to high water mark during low tide and approaching inland positions during high tide. The first engineering test came during the approach to shore. Channel conditions on June 6 featured 4-foot swells and gusty winds that would have prevented operations by smaller landing craft. The DUKWs rode the swells easily, their boat-shaped hulls and adequate freeboard handling conditions that had delayed the invasion by 24 hours. The vehicle's seaworthiness, proven during months of Atlantic testing, enabled operations in marginal weather that would have been impossible for specialized landing craft. Frank Spear had calculated wave impact forces during development, designing the hull to withstand stresses far exceeding normal operation. On D-Day, these safety margins proved essential. DUKWs slammed through wave crests repeatedly during the hour-long transit from transport ships to shore, their hulls absorbing impacts that would have damaged lighter vessels. The engineering principle of overbuilding for extreme conditions validated itself under combat stress. The beach assault revealed the full strategic value of DUKW engineering. At Utah Beach, German defenses had been planned around the assumption that Allied forces would require time to establish beach supply dumps before advancing inland. The 4th Infantry Division, supported by DUKW logistics, maintained continuous advance without the operational pauses German defenders expected. Ammunition, medical supplies, and communications equipment flowed directly from ships to forward positions. Major General Raymond Barton, commanding the 4th Infantry Division, observed DUKW operations from his command post 500 yards inland. His after-action report captured the tactical revolution the vehicles enabled. Traditional amphibious doctrine required consolidation at the beach before inland advance. The DUKW eliminated this vulnerability by making the beach irrelevant. Supplies flowed continuously from ship to front line, enabling sustained pressure that German defences could not counter. The engineering principles that enabled this capability traced directly to decisions made during prototype development. The dual propulsion system allowed smooth, transition from water to land without operator difficulty. The central tire inflation system provided optimal traction on wet sand. The waterproof electrical system functioned reliably despite constant spray and immersion. Each technical innovation contributed to overall reliability that proved decisive under combat conditions. Dennis Pulliston, observing operations from a command ship offshore, documented the performance of systems he had helped design 2 years earlier. The rudder system provided precise steering in rough water during approach. The bilge pumps handled water intrusion during violent wave impacts. The hull shape shed water effectively during beach transition. Most importantly, the simplicity of operation allowed stressed combat drivers to manage complex amphibious procedures without error. By noon on D-Day, DUKWs had delivered over 800 tons of supplies to Utah Beach, more than double the tonnage possible with conventional landing craft in similar conditions. The continuous flow eliminated the traditional beach bottleneck that had characterized every previous amphibious operation. German artillery, targeted at expected supply dumps, found only empty beaches as DUKWs dispersed supplies throughout the beachhead. The medical evacuation capability demonstrated another dimension of DUKW engineering value. Wounded soldiers were loaded aboard DUKWs at aid stations inland, transported directly to hospital ships offshore, and delivered to surgery within 20 minutes of injury. The stable platform provided by the DUKW's hull design allowed medics to treat patients during evacuation, beginning life-saving procedures before reaching hospital facilities. Dr. Captain James Morrison, Chief Medical Officer for the 4th Infantry Division, documented casualty evacuation rates that exceeded all previous operations. The DUKW eliminated every delay in the evacuation chain. Wounded were picked up at company aid stations and delivered directly to operating rooms aboard hospital ships. The mortality rate from delayed treatment, significant in every previous amphibious operation, became negligible. The engineering robustness of DUKWs proved essential as operations continued beyond D-Day. The vehicles operated continuously for 72 hours, transporting supplies during the day and evacuating wounded at night. Salt water, sand, and constant operation would have disabled less robust equipment. The marine-grade electrical components, oversized cooling systems, and redundant bilge pumps maintained functionality under conditions that destroyed conventional vehicles. Maintenance procedures developed during testing proved their value under combat stress. Each DUKW company included mobile repair units with spare parts and specialized tools. Engine problems were resolved by swapping complete power plants from damaged vehicles. Hull leaks were sealed using marine repair techniques. The standardization of components meant that several damaged DUKWs could be cannibalized to create fully functional vehicles. Technical Sergeant William Hughes, maintenance chief for the 459th Amphibian Truck Company, reported repair statistics that amazed logistics planners. We maintained 90% operational readiness throughout the first week of operations. Hull damage was sealed in the field. Engine problems were resolved by component swapping. The engineering redundancy built into the vehicles made field repair practical under combat conditions. The strategic impact extended beyond individual beach operations. DUKWs enabled Allied forces to establish supply lines without capturing ports, fundamentally changing the strategic equation in Western Europe. German defensive doctrine had assumed Allied forces would require major port facilities to sustain large-scale operations. The artificial Mulberry harbours, combined with DUKW logistics, made this assumption obsolete. General Dwight Eisenhower, observing DUKW operations during his visit to Normandy on June 8, understood the strategic implications immediately. His aide recorded Eisenhower's assessment: "These vehicles have solved the fundamental problem of amphibious warfare. We can now establish and sustain major operations on any coastline, regardless of port facilities. The strategic flexibility this provides will determine the outcome of the European campaign." The engineering principles demonstrated at Normandy influenced military equipment development for decades. The concept of dual environment capability became standard for subsequent amphibious vehicles. The emphasis on simplicity and reliability guided specification development for all military equipment. Most importantly, the validation of civilian innovation in military applications permanently changed procurement procedures. Production statistics revealed the industrial achievement the DUKW program represented. By June 1944, General Motors was producing over 1,000 vehicles monthly across multiple assembly plants. The Pontiac East facility alone delivered 300 DUKWs per month, each vehicle tested extensively before military acceptance. The St. Louis plant produced an additional 400 vehicles monthly, while the Yellow Truck and Coach facility contributed 200 monthly. Quality control procedures developed during early production ensured consistent performance across all manufacturing facilities. Each DUKW underwent water testing in specially constructed tanks that simulated ocean conditions. Engine performance was verified through standardized procedures. Hull integrity was confirmed through pressure testing. Only vehicles that passed all specifications were delivered to military units. The engineering team maintained oversight of production throughout the war, identifying problems and implementing solutions across the manufacturing base. When hull cracking appeared in vehicles produced at one facility, metallurgical analysis revealed improper welding procedures. Corrective training eliminated the problem within weeks. When electrical failures increased in another production batch, investigation traced the cause to substandard components from a specific supplier. Alternative sources were qualified immediately. This systematic approach to quality management ensured that DUKWs performed reliably, regardless of which facility produced them. Vehicles manufactured in Michigan performed identically to those produced in Missouri. Standardization achieved across multiple plants and thousands of workers represented industrial coordination that had never been achieved in peacetime production. The Pacific Theater provided the ultimate test of DUKW engineering under extreme conditions. Operations in the Marshall Islands, Saipan, Guam, and the Philippines subjected the vehicles to coral reefs, tropical storms, and volcanic beaches that challenged every aspect of their design. The hull shape that had proven effective in Atlantic swells handled Pacific surf with equal capability. The tire pressure system adapted to coral sand as effectively as it had to Norman mud. Major Robert Patterson, commanding the 773rd Amphibian Truck Company during the Saipan operation, documented performance under extreme conditions. "We operated in surf that would have destroyed conventional landing craft, across coral that shredded conventional tires, and in heat that disabled standard automotive equipment. The DUKWs continued functioning because every component had been engineered for conditions worse than reality. The central tire inflation system proved particularly valuable in Pacific operations where beach conditions varied, and dramatically within short distances. Coral sand required low tire pressure for traction and flotation. Rocky areas demanded higher pressure to prevent tire damage. The ability to adjust pressure while moving allowed operators to optimize performance continuously as conditions changed. Cooling system. Redundancy became critical in tropical operations, where ambient temperatures exceeded design parameters. The dual cooling capability that had seemed over-engineered during development proved essential in Pacific heat. Air cooling handled normal operation. Water cooling prevented overheating during extended low-speed operation in coral lagoons. Without this redundancy, engine failures would have disabled entire operations. The waterproofing standards developed for Atlantic operations exceeded requirements for Pacific conditions. Electrical components sealed for channel spray remained functional after complete submersion in coral lagoons. Wiring routed through waterproof conduits survived months of tropical humidity. Battery compartments designed for occasional splash continued operating after repeated flooding. Statistical analysis revealed the cumulative impact of engineering decisions made during development. DUKW operational readiness rates exceeded 90% throughout Pacific operations, compared to 60% for conventional amphibious vehicles. Mission completion rates approached 98%, with mechanical failures accounting for less than 2% of operational delays. Most significantly, Casualty rates from vehicle-related incidents remained negligible despite extreme operating conditions. The maintenance philosophy established during development proved adaptable to Pacific conditions. Mobile repair units accompanied DUKW companies, providing immediate response to mechanical problems. Spare parts logistics ensured component availability at remote locations. Most importantly, the simplicity of DUKW systems allowed field repairs using standard tools and techniques familiar to any automotive mechanic. Sergeant First Class James Rodriguez, maintenance supervisor for Pacific DUKW operations, documented repair procedures that validated original design decisions. We rebuilt engines using standard truck parts. We patched hulls using boat repair techniques. We rewired electrical systems using automotive components. The vehicle was complex enough to perform its mission, but simple enough to repair anywhere. The supply chain supporting Pacific DUKW operations demonstrated the industrial depth required for global warfare. Spare parts manufactured in Detroit reached forward bases in the Central Pacific within weeks of production. Quality control standards maintained consistency across thousands of components sourced from hundreds of suppliers. The logistics network supporting DUKW operations was itself a testament to American industrial capability. By early 1945, over 15,000 DUKWs were operating across both theaters, enabling amphibious operations that would have been impossible without their capability. The vehicles had participated in every major Allied landing from Sicily to Okinawa, delivering millions of tons of supplies and evacuating hundreds of thousands of wounded. The engineering innovation that had emerged from a yacht designer's office had become an essential component of Allied victory. The final validation of DUKW engineering came during the invasion of Okinawa, the largest Pacific amphibious operation. Over 800 DUKWs participated in the initial assault, delivering supplies to forward positions while under fire from Japanese artillery. The vehicles operated for months in conditions that combined every challenge encountered in previous operations: rough seas, coral beaches, tropical heat, enemy fire, and continuous operation tested every aspect of the design. Colonel Frank Armstrong, commanding amphibian forces at Okinawa, reported performance that exceeded all expectations. The DUKWs operated in conditions that disabled every other type of equipment. They swam through rough seas, climbed coral beaches, operated in tropical heat, and continued functioning under enemy fire. The engineering margin built into these vehicles made impossible operations routine. The strategic impact of DUKW capability extended beyond tactical operations to influence the entire course of the Pacific War. Japanese defensive doctrine had assumed that American forces would require major port facilities to sustain operations. The ability to establish and maintain supply lines without ports forced Japanese commanders to defend every beach rather than concentrating forces at major installations. This dispersal of defensive effort played directly to American advantages in firepower and logistics. Japanese forces, spread across thousands of miles of coastline, could not concentrate sufficient strength to defeat Allied landings anywhere. The engineering innovation that had made trucks amphibious had created strategic options that traditional amphibious capability could never have provided. The technical specifications that had emerged from systematic engineering during development proved optimal for global operations. The 6-knot water speed provided adequate performance without sacrificing seaworthiness. The 50-mile-per-hour land speed enabled efficient highway operation. The 2.5-ton payload capacity matched military requirements exactly. Most importantly, the simplicity of operation allowed rapid training of operators and mechanics. By August 1945, DUKW production had reached 21,147 vehicles, making it one of the most successful military equipment programs of the war. The engineering principles established during development had guided production of thousands of vehicles that performed identically across multiple manufacturers and operating environments. The achievement represented not just mechanical innovation but systematic engineering applied to mass production. The civilian engineers who had created the DUKW concept received recognition that reflected their contribution to Allied victory. Rod Stevens was awarded the Medal for Merit, the highest civilian decoration. Dennis Poulaston received the Legion of Merit for his technical contributions. Frank Spear was honored by the National Academy of Engineering for his systematic approach to complex technical problems. But the greatest recognition came from the soldiers, sailors, and Marines who operated DUKWs in combat. They called them simply DUKs, ignoring the military designation in favor of a nickname that captured their affection for vehicles that had carried them safely from ship to shore across the world's most dangerous beaches. The engineering achievement was measured not in technical specifications, but in lives saved and missions accomplished. The lessons learned from DUKW development influenced military engineering for decades. The principle of dual environment capability became standard for subsequent amphibious vehicles. The emphasis on simplicity and reliability guided all military equipment development. The validation of civilian innovation in military applications changed procurement procedures permanently. Most importantly, the demonstration that systematic engineering could solve seemingly impossible problems encouraged continued innovation in military technology. The industrial achievement represented by DUKW production demonstrated American manufacturing capability that adversaries could not match. The ability to design, develop, and produce thousands of complex vehicles while fighting a global war showed industrial depth that determined the war's outcome. Each DUKW that drove from ship to shore carried with it evidence of a civilization that could transform any challenge into an engineering problem and solve it through systematic application of industrial capability. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.